Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. I'd like to appreciate our members who have been engaging us in the comment section, and also like to kindly request those who have not subscribed to do so. I'd also like to request the members to check our description boxes for various links of other similar discussions we are doing on the concept of electricity and magnetism. Now, in our discussion today, I'm going to look at the concept of capacitors, and our objective today is to identify the concept of capacitors and the electric charge, which we have particularly discussed in our previous videos. Now, we're going to look at how we can be able to quantify this specific aspect of capacitors, and particularly some of the factors which are going to be considered in order to try to measure this specific aspect of capacitance. And then we shall look at one of the examples of course, in terms of a problem set, which is going to form our final bit of this specific discussion. Now, in a sense, I mentioned earlier in some of our discussions whereby we have mentioned in one way or another the concept of capacitors. And I said that particularly capacitor is a device which is going to store what we refer to as electric charge. Therefore, using particularly a summed up or a summary definition, we can refer a capacitor to as a device that stores electric charge. Hope my handwriting is legible. Now, in this specific case, I've just written this one in a summary form because of a space. And therefore, as I've said, we can define a capacitor that a capacitor is a device that stores electric charge. And of course, we are going to see that we can illustratively show this specific type of a device which we have referred to as a capacitor, particularly in trying to show its major components or its structure, which is going to assist us appreciate its specific role. Now, I can give this one as a combination of two charged plates, which are going to be a positive plate, positively charged plate, and a negatively charged plate in the opposite direction. And then we're going to have an insulating material at the middle of this specific section, which is basically going to have a specific term. Now, in this case, we're going to have these two specific connectors, which are going to be basically conductors. And these are going to be wires which are going to be used in trying to connect the specific components of this particular device that we refer to as a capacitor. Therefore, the two plates which have just indicated for positive and negative, these are going to be constituting what we refer to as charged metal plates. And then we shall have this specific material at the center, which is basically going to be an insulating material that we can refer to as a dielectric. Now, in this specific case, we're going to look at how these specific materials are going to affect the concept of capacitance under the concept of, or rather when we're going to look at various aspects which are going to, or factors which are going to affect this specific aspect of capacitance. Now, in a sense, then I've said that a capacitor as a device is going to constitute of these three specific setups of materials for connecting wires, dielectric, and the charged metal plates for the positive and negative respectively. Now, we have different types of capacitors depending on the specific area of application. Perhaps also we can just give particular examples for these specific capacitors just by mentioning them. And perhaps we're going to come across them in some of our discussions, perhaps which are going to be areas of application in detailed form. Now, the first example we can use is an electrolytic. This is electrolytic. So we're going to have an electrolytic type of capacitor, and then we are going to look at other, of course, examples like the ceramic capacitors, and then we are going to look at other examples like the mica. And in this particular case, we're going to see that some of the capacitors are going to be named due to the specific components which have been used. For instance, the one which I've referred to as mica, we have come across this specific kind of a natural mineral which we are going to refer to as mica. And therefore, we are going to expect this specific component of the capacitor which I've given in the middle, referred to as a dielectric, made up of this specific material that we have referred to as mica. And therefore, that's where this specific capacitor is going to derive its name from. Now, some of them that we're going to come across like the Mylar, of course, capacitor. This is going to be a capacitor made up of specific materials like the polyester films, which we are going to come across perhaps in some of our discussions. So this is going to be a polyester film capacitor, which is going to be sometimes referred to as the Mylar capacitors. Now we are basically mentioned the definition of this specific device that we refer to as a capacitor. Now we're going to look at how we can quantify this aspect of capacitance, which perhaps we have defined in one way or another in some of our discussions, and try to see what are some of the formula which we can use in trying to obtain this amount of charge which has been stored in the capacitor. Now the amount of charge which I've mentioned being stored by capacitors can be evaluated, and this is going to be directly proportional. So this is going to be directly proportional to the potential difference between these specific charged plates. So I'm going to give this one in terms of a summary form because of a space. So the amount of charge stored by a capacitor is directly proportional to the potential difference between the plates. And this can be given in terms of a capacitance, which is given in terms of a C, or rather the amount of charge which I've mentioned, which is of course given as Q, is directly proportional to the potential difference between the charge plates, and therefore we can give this particular relationship or a specific amount of charge given as such. So I can indicate that one as formula 1. So from that specific relationship, then therefore we can develop a formula for us in trying to find the relationship between a capacitance and the potential difference. So we're going to have this one given as this, and this is going to imply what we refer to as a capacitance. So this is going to be particularly a ratio, as we're going to see, but this is the amount of charge which is going to be, or rather this is going to be the amount of charge, it's going to be the relationship between the amount of charge stored, and then we're going to see with the potential difference between the two plates. Now in this particular case, then therefore we're going to come up with this specific term, whereby V is the potential difference and Q is the amount of charge. Now I've got what we refer to as the SI unit used to measure this specific, of course, concept of a charge which I've mentioned, and these are going to be given in terms of farads. So this is going to be given in terms of farads. Perhaps in our subsequent discussion, I'm just going to use that particular initial for F referring to as the SI unit for measuring capacitance. Now the aspect of capacitance is going to depend on a number of factors, and therefore we can mention this one as factors affecting capacitance. So I'm just going to give it as C so that we can just have a summary of this. So there are a range of factors which we're going to consider, which are basically going to be affecting this specific aspect of our capacitance, and these are going to be at the area of the two plates which I've mentioned basically for the positive and negative charge plates. We're going to see in this specific case that the larger the plates, they're going to result in more field flux, and therefore that's going to give a particular force which is going to be a field force in this particular case. So therefore we're going to have a direct proportionality relationship between the area of the plates and the amount of capacitance given in terms of a C. And of course, as we're going to see by giving some of the examples later in our discussion, the shape of these specific plates are going to be affecting this aspect of capacitance, and that's also going to be one of the major factors which is going to affect this specific aspect of capacitance. And then we're going to look at the distance of separation between the plates. Now, as the plates are going to be separated from one another, that's also going to affect this specific aspect of capacitance. Now in this case, there's going to be an inverse proportionality in a sense that if the distance is larger, then therefore we're going to expect this field force to be minimized, and therefore the greater the distance, the lower the amount of capacitance which is going to be of course experienced. Now lastly, we can mention, last but not least, we can mention the nature of the dielectric. The nature of the dielectric is going to affect this specific amount of capacitance which is going to be experienced. We're going to see that some materials are going to have a higher permittivity or allowing for more field flux, and therefore that's going to be giving an aspect of a higher capacitance, but we're going to see some of the materials are going to be having different amount of permittivity, and therefore that's going to be affecting this specific aspect of capacitance in this particular case. Perhaps I can. So I'm talking about the permittivity. We have mentioned the concept of permittivity of free space and other related content, which is going to be dealing with this specific wording. Now, in this particular case, then therefore we can develop a symbol relationship from these specific factors which are going to affect capacitance. Now, particularly, we have mentioned the concept of area, which we're going to look at, and the distance of separation. In this particular case, then therefore we can just have this specific conclusion that basically the dimensions or the specific nature and shape of the materials which are being used, especially the plates, are going to affect this particular aspect of capacitance, and therefore we can give a relationship of capacitance as directly proportional. We say that the larger the area of the plates, the larger the amount of capacitance, but it's inversely proportional to the distance of separation, which we can give in terms of d given as such. So therefore, this is going to form another relationship which we can look at, particularly in terms of capacitance. And therefore, considering the area of the plates and the distance, we can have another relationship, or we can develop an equation for this one, whereby C is having a direct relationship to A over B by introducing a constant. Now, this specific constant is going to be a permittivity of course, which we had mentioned. And this permittivity can be given in terms of the epsilon naught given as such. And this is a constant given as 8.85 times 10 negative 12 Coulomb square per Newton meter square. So I've mentioned the concept of permittivity of free space in some of my previous discussions, and therefore we are going to understand this specific aspect of permittivity from this specific context. Now, in this case, then therefore we can have this version of the equation. Let's have this one as our equation 1, equation 2, and therefore we can have our equation 3 by giving it as a capacitance is equivalent to the permittivity times the area all over the distance. And this is going to form our essential equation for equation 3, which we are going to use later in some of our application areas. For instance, I can just give an example of this for just illustration purposes. If we are required to calculate the capacitance of a parallel plate capacitor whose plates are given by a specific dimension and a distance of separation, perhaps I can just give this one as a rough illustration so that we can use this one as an example. So we're having these two plates which are separating the two positively charged plates and the negative charged plates. And we have been told that there's a distance d of separation, and then we're going to have an area given as A. So this is going to be the distance of separation. So having been given the distance of separation and area, then therefore we can use this constant as one of the factors in order to calculate this particular concept of capacitance. Now, in this case, the area has been given as 1.8 centimeters by 2.0 centimeters, and then the distance of separation has been given as 1.2 millimeters. So in this particular case, I like to grant emphasis especially on the standard units which are being used especially for the area and the distance, and therefore having taken care of that, we can be able to evaluate this specific question set. So we're going to have capacitance given in terms of 8.85, which is our permittivity times 10 negative 12. Perhaps we can include this one so that we can be able to develop the final part of the dimensions which we're going to express our capacitance. So in this case, it is going to be a constant times the area. So in this case, for us to find the area, it's going to be 1.8 divided by 100. So we're going to convert this one directly into meters times 2.0 divided by 100, and this is going to be meters. So in this case, this is going to be all over the distance of separation, which is 1.2 times 1 over. So we're going to also form this one in terms of meters. And if we try to look at this, therefore, this is going to be given in terms of these particular units, which are going to be given if we try to look at this one, of course, we're going to have the remaining of this square of capacitance given in terms of C, and then we're going to have the newtons remaining together with the meter. Remember, this is going to be a numerator, and therefore the square of these 2 meters are going to be cancelling out. So we're going to have this specific value given for 2.6. So I'm finding this specific value. So kindly do, in case you find a different value, I always recommend that we do an adjustment, perhaps in giving us a feedback in the comment section. So I'm going to have that one given in terms of 10 negative 11. This is going to be squared all over Newton meters. Or this one can be given in terms of farads, which we said are the SI units, and therefore this is going to be 2.655 times 10 negative 11, given in terms of farads. So in some cases I've mentioned that the farads are large units. Of course, we're going to have some of the subdivisions of this specific unit in terms of microfarads, nanofarads, and the picofarads. And these specific previces are going to be assisting us in trying to adjust this specific unit in case we come across a device which has got that specific definition. So in this case, I'd like to encourage our members to kindly check our description boxes for various links of other videos. But I assume that we have known what capacitors are, the different types, and perhaps how we can be able to evaluate this aspect of our capacitors given a problem set. So that is it for now, guys. By God bless you. Catch us in our next video.